This is part 2 in a series of videos in which I'm attempting to demonstrate how to use a logic analyzer. This is not the only way of using a logic analyzer, but I'm just going through the basics, and hopefully this information will be of use to anyone that's starting out or has picked up a logic analyzer off eBay and is trying to figure out how to use them. They are extremely powerful machines for diagnostics, development, fault finding, and unfortunately they do tend to get underused. There's a lot of features in logic analyzers like this that never get used because usually the owner's not aware that the machine can even perform the functions, but also the user manuals are not always particularly clear. Now, I'm not trying to criticize the writers of the manuals for these machines. I really do not envy the person that had to write the instructions for using the trigger on these. And I say that because there are so many different ways that a trigger can be used. There's pretty much an infinite number of ways to configure it. So what I'm going to be doing through the series of videos is going through the basics. In the first video I showed how to really set up the basic analyzer from scratch, setting the inputs, that sort of thing. In this video I'm going to extend and expand on that a little bit, how to set up the input levels and using things like terms and labels within the analyzer to help clarify its use. And then in the subsequent videos that will be following, I'll go into the features of the analyzer, such as complex triggering and this sort of thing, in much more detail. So for this one, the first thing I want to look at is the signal level that you feed into the analyzer. Most of the time they're hooked to something like a TTL system, so the standard default levels work fine. But if you're developing a system or you're using an FPGA or something like that, then you may well need to change the levels. So as part of this series, what I've done is make up this simple board. It's just a 16-bit binary counter with a clock, a ROM, and I'll be using this throughout this series for various demonstrations. This first demonstration, I'm just using the clock. It's going through a pot, and this will enable me to vary the clock level, the signal level. If I turn the power on to this board and we look at the scope, you'll see that we're getting a stream of pulses, and if I turn the pot down, the amplitude of those pulses will drop accordingly. This is going to be used to demonstrate how to set up the input levels on the analyzer. So we'll get the analyzer powered up. I'll fast forward through the boot up. Okay, and we'll load the test configuration that I created in the previous video. Okay, so we've got our configuration loaded, and if you recall, there wasn't a great deal in here. I just had address data and one other control line set up. What I'm going to do in this video is look at the input level. I'll zoom you in a few minutes, but what I'm trying to do here is demonstrate that the input levels fed to the analyzer not only need to be a particular level in terms of their amplitude, but also that you can adjust them if you need to. So although you may not be able to see it, I'll zoom you in a minute, but each of the pods has got a symbol above it, so each of the pin designators has got a symbol, and in this case the far right one is showing an up and down arrow, and it shows the activity on that line, so it's showing that the line is toggling. If I turn the power off to our test board, you notice that disappears. So what I've got set up here is the clock is going to our bit 0 input on pod 1, and when we feed this in, you'll see the level start to toggle. So I'll turn it back on and you'll see the arrows reappear. But what I can do is adjust this input level using the pot, I'll start to turn it down, and if you keep an eye on the analyzer, you'll see that arrow will eventually disappear. So it's now disappeared. If I turn, and if you look at the scope, you'll see the signal amplitude is much lower. If I turn the pot back up, you'll see that the arrows have reappeared on the analyzer. So I'll zoom you into the analyzer screen so you can see it better, and I'll repeat that test. Okay, so we're looking at this area of the screen. You'll see there's the up and down arrow showing, and I'm now going to turn the pot back down on our demo board. And as I turn it down, you'll see that at some point the arrows disappear, so they've now stopped. This has stopped toggling the input to the analyzer. So in other words, the analyzer can no longer see this signal. I'm just going to change the machine to timing mode so we can actually run it without a clock being fed into it. If I go to waveform and hit run, notice that we're just getting zeros on data and address. If I turn the pot back up and we run this again, notice we're now getting an incremental value. So basically it's toggling between 1 and 0 as it's a binary counter, and so the clock is just rising and falling, so it's alternating between a 1 and a 0. If I run it again, toggling of the input, and if I turn the pot down, notice we're getting all zeros every time. If we go back to the format, you'll see the arrow's gone. I'll turn the pot back up and it comes back. So you can adjust this. In this case, if we turn the pot down until the arrows disappear, assuming that's the system now that we want to work on, what you can do is come down to the particular pod that you're using and select the designator to the right of the pod. In this case they're both set to TTL, and this is for the entire pod. You can't do it on individual bits, but you can do it for individual pods. If you select this option, you've got two built-in levels, TTL and ECL, but you can also go down to user and you can set the particular level that you want. So in this case, what I'm going to do is set 500 millivolts as being the threshold. So what you're doing here is you're setting the threshold between what represents a 0 and what represents a 1. And notice now that our arrow has come back. And if we go back to waveform and run it again, you'll see that it's now able to capture that data reliably again. So all you need to do is make sure that the value that is being fed into the analyzer in terms of the amplitude of the signal is suitable for the particular system that you're working on. If it's TTL, you can just leave it at TTL, although having said that, some TTL ICs have different levels to others and do vary quite a bit, but in general the TTL will work 99% of the time. But if you're getting odd behavior of your system, it's always worth coming in, selecting one of the bits as we've done here, and we notice that at the moment the input is not toggling, whereas if we come into this setting, select the input level we want, which can be anything we want, notice it's now toggling again because we've redefined the thresholds. I'll set that back to TTL. Okay, now the next thing relates to bus polarity or signal polarity. So I'm just going to move the camera and rearrange the inputs a little bit, and I'll demonstrate how to set up the input polarity for each of these signals. Okay, so what I've got set up here is a simple breadboard. All the inputs to pod 1 have a flying lead on them, and all of the bits apart from bit 0 are connected to ground, and bit 0 is connected to 5 volts. And if we look onto the analyzer screen, we'll see that bit 0 is showing as high, so it's just represented as a fixed bar. It's not toggling, so it's not showing arrows, it's just showing a fixed level, and all the other bits are set to low. If I move that bit to ground, you'll see that that will briefly show an arrow and then show ground. And if I move it back, again you'll briefly see an arrow and then it will show a high. If we capture data, and again I'm still on timing mode here, so it doesn't need a clock, but notice now that every time we run we are getting an address value of 1, which is correct of course. Now sometimes you'll be working on machines where the bus is inverted, so a machine like a PDP for example, a 0 voltage on the bus actually represents a binary value of 1, and sometimes you'll want to capture data using that polarity. You're interested in the actual signals, but sometimes it's the actual data values that you're trying to capture or that you're interested in. So for example, if you're reverse engineering firmware, you're probably more interested in the actual values, or what the bus values represent, rather than the signal levels themselves. So in this case what I'm going to do is swap over the plus and minus signals. So I'm going to move all the input bits that are currently connected to ground to 5 volts, and I'm going to move bit 0 to ground, so it will effectively invert this data, which is what you would see if you were using an inverted bus. I'll just move all these across. Okay, so I've reversed all the connections, so this is how this same data value of 1 would be represented on the actual bus of a PDP machine, which uses negative logic. And if we look on the analyzer, you'll see that all the high order bits are showing as high and bit 0 is now showing as 0. So if we rerun this capture, we're now getting a value of FFFE, and obviously that's not really what we want. We want it to show a value of 1. There's a very easy way of changing this. If you go to the format menu and come down to address, and you see this plus sign, so there's a plus in each of these boxes. If you just select that and press select, it will change to a minus sign, and it's as simple as that. If we now go back to waveform that we've captured, notice it's now showing a value of 1. So I'll zoom the camera in again so you can see it a bit more clearly. Okay, so hopefully that is a bit clearer. So you can see here that we're getting a value of 1. If I capture it again, it's the same, but the value actually being fed in is still FFFE. I haven't moved the jumpers, and if we go back to the format, you'll see that that address is inverted. If we change it back to positive and then go back to waveform, you'll see that the value is again showing FFFE. So if you're dealing with inverse values and negative logic, then all you need to do, go into the format menu, invert whatever bit or bits you are looking at that you need inverted, and that will then show the value in its inverse form, and that can make life a lot easier if you're trying to work on reverse engineering something using a negative logic bus. Okay, so the next thing I want to look at is the use of symbols within the analyzer. In the coming videos I'll be going into some detail with complex triggering, and it would make it far easier to explain how to do that on this analyzer if I first explain the use of symbols. So if we go to the trigger menu and we scroll down, as I demonstrated in the previous video, you can, if I want to do, I'll change back to state mode because it makes this explanation a lot clearer. So we'll change the analyzer back into state mode. This does apply to timing mode, it's just easier to explain if we're using the machine in its state mode. And what we can now do is go back to trigger, and we have the terms that we saw previously. And before I start, I should just, I think, take a slight detour here and explain that the terms that we're seeing, so down here we have all these terms that we can apply, and we use these within the sequence that we're creating for the trigger. Don't worry if this doesn't make sense yet, it will hopefully make sense as the videos progress. But sometimes you want to use this machine almost like it's two completely separate analyzers, but using the data captured from both in a comparative mode. Or it might be that you want to use symbols or terms that you've defined in one in the other machine. The way you go about doing that is, if we go back to the setup menu, notice that Analyzer 2 here is set to off, but if we turn it on, we'll turn it to state mode as well, and then we go back to the trigger, notice that down here this is now changed, and if we select assign, we can now determine which of the two machines these terms are assigned to. It can only be one at a time, so as you select each one it will move from one machine to the other. So if we want to, for example, set C into machine 2, just select it, press select, and notice it moves across to the other machine. If you want to move I, do the same thing. If you want to move it back, select it in the other machine, and notice we can now move them back. So you can just toggle them back and forth between the two machines. So though you can define them however you want, you can only assign them to one machine at any one time. I'm not going to be demonstrating that here, so I'll turn the second machine back off. But if we now go down to the trigger menu, what we have here is the ability to trigger on certain values. So if you aren't interested in a value, just set it to don't care using an X. You can mix and match these, so X1 means don't care about the first part, but the second part has to be a 1. So you can, it is very powerful just using a very simple absolute value. But quite often as you get into more complex debugging, what you want to be able to do is keep track of certain ranges of values so that they make sense. It might be you have source code, for example, that calls a certain address a certain thing. You can of course just set an address as a trigger point, so if we just enter whatever value we want, then what we've done here is set the address to a particular value. You also have the ability to set ranges of values. So in this case we could set a range of addresses, so it might be we want to capture data for a particular ROM and we just set its start and end address. Or you can use timers. So the timers are, there are two free running timers, or times you can start and stop within the context of a trigger sequence, and you can actually use those timers as trigger points for the analyzer. So you can start a timer, stop a timer, and when it reaches a certain value you can use that value to trigger the analyzer. But I'll come back to that in a future video. For now what I want to do is just try to explain how we can use particular value to trigger the analyzer. So if we come back up and we'll simplify the trigger value that or the trigger sequence that we're using, and in this case I'm going to set so that this particular trigger for our machine is set to occur one time. So the way this trigger is set up, if the A term, which is set to an address currently of 3651, occurs one time, it will trigger the analyzer. So in other words, if the input to the pod 1 pins ever reaches that value, then it will trigger the analyzer. So in other words, we can search for a particular address and access of that address. But it's a bit, it means you've got to remember the value, remember the address, and sometimes it's just easier if you can give the particular addresses or range of addresses a name. If you come up to the format menu, notice this value or this menu is called symbols, and if you go into that, okay, so this is the user symbol table. Symbols in the analyzer are a bit like defines in a programming language. They allow you to give names to values, and it does make using the analyzer much more intuitive and clearer, especially if you're doing something like reverse engineering software within a system. But what you do, and incidentally you can have or use one of the inbuilt symbol databases which allow you to share symbols easily between different projects. But what I tend to do is save symbols within a given project, and then I will rename that project and save it as a new project when I want to move on. But what you do to create a symbol is set the symbol width that you want to use. In this case we'll set it to 16 bits because I'm going to use this to look at the address bus, and then go down to new symbol, press select, and it wants a name for the symbol. So in this case our first symbol will be, for example, to access a ROM within the system, so we'll call it ROM1. Press select, and now we move on to type, and it can either be a pattern, which is just basically a value for that input, or a range, in which case it's going to trigger, or it's going to be valid if the input value is between the two values that you select, including the two values, so it's inclusive of the values that you set. We'll start with the pattern initially, and if I set this to 8000 for example, then this means that any time we access a value of 8000, it is going to trigger if we use this symbol. Okay, then press select, and you can then come back, add a symbol. We'll call this next one ROM2. Hit select, and we can now do something similar with ROM2. So it might be we want to define it as the next ROM, but of course that's not really how you would normally access ROMs. You'd normally access them as a particular range, but it depends on what you're going to use the symbol for. So in this case what we'll do is we'll say it's a range, and we'll say this is going to be valid from 9000 to 9FFF, and so this will be valid any time we're within that range. Whether it triggers the analyzer or not will depend on what you're using the symbol for. We'll come back to that later on. If you want to come in and change the symbol, you can do that any time you want. You can change the value, or you can change the type. So in this case I've changed my mind and decided that I want to use ROM1 as a valid value whenever we are within the range 8000 to 8FFF. And really the way to look at these is it's kind of like a macro, and it becomes true if the input value falls within the range that you set, or if it equals the value you set if it's just a pattern. Now when you come back to trigger, you can make... Okay, so back in the trigger menu, we can now make use of those symbols that we've created. If we go back down to the value we had before, remember this is the value we had set, and it's the value the analyzer will trigger on if we start it running. But if we want to use a symbol, all we have to do is go up to this field. Currently it's set to hex value. If we select that and go down to symbol, at the moment it's still showing the same value. It's saying 3615, and it's an absolute value, so in other words it will trigger on 3615. But what you can do is come into this value, hit select again, and we can now select one of the symbols that we've created. You can also set an offset. I don't want to use an offset here, so I'm going to set that to 0, and then you select whichever symbol you want to use. Absolute is a standard one, it's always there, and it just means the value that you enter. So in this case I'm going to use the ROM1 symbol. Hit done, and notice now it's saying ROM1, so, and with a value at the end of plus nothing, so in other words the offset we've set to 0. So as things stand at the moment, if we were to start this running, it would be triggered because we're using term A in our trigger. Then whenever we hit the range of values within the ROM1 symbol that's been defined, it would trigger the analyzer. And of course you can go back to the symbols anytime you want and change the values. So in this case, as you can see, ROM1 is going to be anywhere between 8000 and 8FFF. Go back to trigger, and if you want to change this, you can come in and modify it, or it might be that what you're going to do instead is set up the B term, and in this case we're going to select ROM2. So now notice we have ROM2 set, again with an offset of 0. And if we want to now, we can just come up and change the actual term that we're using. So we'll change this to B, and we're now going to trigger on B, which in this case is ROM2. You can set sequences and various complex triggering, which we'll start to look at in the next video. But just bear in mind that symbols are very powerful and give you a lot of control over what it is you're actually trying to trigger on. And of course you can use symbols for all of the fields. It's not just a particular field. It might be that when you do set them up, you've got to use different symbol widths. So it might be you want to set a 1-bit or 8-bit or whatever. But as I said, it's a very powerful system, and it makes fault finding and reverse engineering much easier. And of course these values are shown whenever you make a printout, so it's a bit like creating your own pseudocode within the system. Okay, so that's it for this video. In the next video we'll start to look at more complex triggers. If there's anything in particular you want to cover with these machines, then please leave a comment. But hopefully as the video series progresses, everything will start to come together and all this will start to make much more sense.